Hello everyone, welcome to MINDSPAN Education. This is our series of calculation optimization for GATE DA, and till now we have already covered function of single variable, limits, continuity and differentiability and other topics. Our today's topic is optimization problems. Optimization that involves one variable and how we use single and double derivative test to optimize those problems to find the optimum value of any variable that we will see in this video. So, our topic name is optimization using single variable only. Single variable functions optimization we will see in this video. Single variable. So, this is our topic today. Here in this topic what we are going to learn basically is, in last video we saw maxima and minima. We also saw how when a function is increasing, when a function is decreasing, what are those conditions when we say that function is strictly increasing or increasing, and what are those conditions that we check whether a function has maximum or minimum value at any given point in the domain. All these things we have already seen in the last video. So, this video is strictly related to the last chapter. So, if you have not gone through that video, I would recommend you to go through last few videos in this series, then come to this topic. Okay. So, in this topic what we are going to learn is, sometimes we see real life problems where we need to optimize. Suppose let's say we have to make a fence. Let's say we have to make a fence. I will give you an example by which I will explain what optimization means. So, let's say this is a river. Okay, this is a river which is flowing, and beside this river we have a field. This is a field. In this field we have gotten, let's say, 2400 meter of fence. For fence we are trying to fence here to make our dedicated area, and one side is already a river. So, we have to fence this from three sides. We have to fence it in such a way that area of this fencing becomes maximum area. But the condition is we cannot exceed, we have only this much of fencing material. This is length of the material, only 2400 meter. So, how do we fence? What length and breadth we should choose so that our area becomes maximum? I will give you an example. Let's say we choose 100 meter for the width. 100 meter will go this side also, and rest 2200 meter will go here in length. So, what will be the area now? Suppose the fence is rectangular or a square. The fence cannot be of circular or any other shape. So, what will be area become? Area will become 2200 into 100 meter square. This is one guess that we guess that let's take width 100 meter and length 2200 meter. So, we can exhaust all our fencing material 2400 meter. So, area will become 220,000 meter square, right? But some other person will come and they will claim that this area is not the maximum. I will take the fencing as length as let's say 800 meter and width also 800 meter. Let's say someone will come and tell you this. Using this also we are going to get 2400 meter fencing material, but the area will become 800 into 800, right? Length into width meter square, and by this guess we are going to get 64 640,000 meter square, which is obviously greater than the last guess that we had 2200. This is greater. So this was a poor choice for the fencing, and this was relatively better choice to take 800 meter. So one thing we can do is to guess all the values starting from 0 to 2400. We guess all the values. We will take all the values that are possible from 0 to 2400, and we try to calculate area everywhere, and whatever maximum area we get, that will be our answer. But that is practically not possible, because there will be infinitely many real number between 0 to 2400. So this is, now you understood what type of problem we are going to solve using this optimization technique. Here we are optimizing the area by making adjustment to the variables. Variable means length and width, so that we get maximum area with some condition. Condition is this, that length, overall length, combined length of the material should not exceed 2400 meter. This type of problem is called optimization problem. It will come in different shapes and different structures, but the core logic will remain same. So how do we solve this kind of problem? We are going to see in this video. So let's see what we do here. What are the steps? What we do? First, let me enumerate the steps. What we do in this kind of problems. First we calculate. First, we draw the diagram, so that we understand completely what the problem is saying, what we are trying to figure out. First, we draw the diagram. Second, we define the variable. We can say we identify, identify unknowns. We can say variables. What variables? Like here we had length and width, width and length. So in all the cases, we might have radius somewhere, we might have height. Those kind of variable we first define. And third, we try to express in algebraic form, or you can say that we try to find the function that we need to optimize, optimization function. Okay. And fourth, we calculate the derivatives to identify maximum or minimum value. Right? These are the steps that we do in optimization problems. Why I wrote all these things? So that you get an idea, you don't get confused while solving the problem, and you do it in a structured manner. First, we draw the diagram so that we understand the problem completely. Then we identify what are the variables. Then we express those variables in form of function, that is fx, and derive. After that, we calculate the derivatives like say f dash, f double dash, whatever we need, we'll calculate them, and then based on their nature, f dash and f double dash x, we try to find maximum and minimum value. And how do we find maximum and minimum value using first derivative and second derivative tests? That we have already seen in last video. So in this particular topic, I am going to take a lot of examples and try to understand this topic through solving those examples. So let's take one example. The first example itself, let's try to solve this first example. Let's try to solve this using our method. So what is the question? We have a river, let's say, and this fencing we are going to do. Okay, total length of the fence we have 2400 meter. So first we draw the diagram. This is river, and this you have to assume that this is a straight line. Okay, otherwise we will not be able to form a rectangle or a square. So in this particular example, we are going to do all the steps. First step, draw the diagram. We have drawn it already. So we have to find maximum of this area of this fenced land. Let's call it A. We have to maximize this. This is our target in this problem. Second, we have to find variables. What are variables? What are the things that we are assuming? Here we are assuming that let's consider x is the width and y is the length. Then this will also become x since it is rectangle. So this x and y's are variables. Here x and length is y, and these x y becomes variables. So what these things, second step was to identify the variables. What we assumed here, x and y, these were the variables for this particular problem. It may not be very easy in difficult complicated problems, but here it is easier. In other examples we will take, we will try to see how we calculate, how we identify unknowns for difficult problems. Okay, now what we have to, we did this step, we did second step. Now third step, express in algebraic form the function that we are going to optimize. What functions here, what function do we have here? Here we have area as x into y. This will be the area of the fenced land, and we have to maximize this area, maximize area, right? This is our goal. So we have already expressed in algebraic form a equal to x and y, but here you can see that our function is not single variable. We need this in single variable function, right? This is currently not in single variable function form. So any guess how we can convert this to single variable? We have to use this extra information that total length of the material is only 2400. So we can write that x plus y, 2 times x plus y, that is x, this side x, width will come twice, 2 times x, and length will come once. This should be 2400. It should not go beyond 2400. We do not have that much of material. Now using this a equal to xy and 2x plus y equal to 2400, we have to express a in single variable form. From here we can say that we can write y equal to 2400 minus 2x, right? Now put this y in area. We will get area as function of x equal to x into y. X into y is 2400 minus 2x. Now we have a single variable area function. This is 2400x minus 2x square. This is our ax. We have to find maximum and minimum value of this function, right? This function. So now we have conceptual. Now we have formulated this problem in the algebraic form. Next steps are similar as we did in previous lecture. We have to find the maximum value of a area function. So how we do that? We first calculate first derivative of x area. This will become 2400 and this will become 4x. Now we equate a dash x to 0 to find critical points, or you can say the standing points. Okay. So by equating this to 0, we will get 2400 minus 4x equal to 0, which will give us x equal to 600, right? Now, since we got x equal to 600, but we do not know whether area will be maximum at x equal to 600 or minimum. So, for that we will use second derivative test. We will calculate another derivative of area function. Here we will get minus 4, right? Since this is less than 0 for all x, so we can say that this area function at x equal to 600, we are going to get a maxima, that is maximum value. We have already discussed this in last video. Since a double dash x is less than 0, which will give us maximum value. So what will be the maximum area? First x equal to 600. What we got here? Let's see. First we got x equal to 600. So what we are going to get? Y equal to 2400 minus 2x, that is 600 into 2 times 1200. So we are going to get 1200 meter, right? And x we already got 600 meter. So the fence that we had created, in this fence here, if we take 600 meter width and 1200 meter length, then we are going to get maximum area, which will be equal to 1200 into 600, 7200, 720,000, right, meter square, which is maximum. You cannot get more than this by assuming any value. This is maximum area possible for this given constraint. So by guessing what we were getting, let's check till where we had reached. We had reached 220,000, then 640,000, but here we have got 720,000. This is obviously the maximum value possible, right? So this is our answer. We can say that by taking length 1200 meter and width 600 meter, we are going to get maximum area, right? So this is a very simple question, but this is very important for understanding the topic. This is how we solve optimization problems. See what we did here. First we formulated the problem in pictorial form so that we understand exactly what this question is asking. Second, we defined it in algebraic form, the function that we are going to maximize or minimize, that is optimize. And later we manipulated this x and y based on the given constraint, that is total length equal to 2400, length equal to 2400. Using that, we manipulated this x and y to make this function, area function, as single variable, so that we can apply first and second derivative tests to find maximum and minimum value of this function. And later on we simply applied first and second derivative test to find out what will be maximum value and at which point this maximum value is going to reach. So this is how we calculate maximum and minima. This is how we optimize any function given with given constraints and in these forms. I will take one more example to make it more clear so that you don't get confused later on. So take example 2. Let's first define the problem. Let's say we are going to create a cane. This is a cane means can, right? Condition is its volume should be 1.5 liter. This is the condition, and we have to minimize the cost. Minimize the cost of manufacturing. This is the condition. We have to make a can of volume, and this is cylindrical can for your reference. Cylindrical can with a volume 1.5 liter. This is a hollow can uh, with a volume 1.5 liter, closed from all direction. Okay, hollow can. And condition is we have to minimize the cost of manufacturing. So this is the problem. We have to make a can of 1.5 liter volume and minimize the cost of manufacturing. In what actually what this problem is asking is what dimension we should take for this can, like radius and height, so that we get minimum cost. Cost is like cost of material. This is the sheet that we use to create this can, right? So this is hollow can, so the sheet we used to create this can, material, cost of material should be minimum. Okay, so we have to find these dimensions, radius and height of the cylindrical can, so that we spend minimum to manufacture this. This is the problem, right? So first step is already done. Step 1 already done. We have already drawn the diagram, and we have already understood this problem completely. So first step done. Step 2 is to find unknowns. Unknowns and variables. Here we have radius r, and let's say radius r, unknowns we have radius r and height h. This thing we have to calculate here, correlate and calculate. So let's see how we are going to do that. First, we have to minimize the cost. So we have to calculate the function that we are going to optimize. So function is, let's say, overall area. This is the area, surface area. We can say this is surface area. Amount of material we are going to need is the surface area of the cane from all direction, from all up and bottom, and the curved surface area. So surface area of this cane will become, you can say there are two circle, one from bottom and one from top. Okay, so 2 pi r square. Let's say we have r as the radius and h as the height. This is what we assumed here. So surface area will become 2 pi r square, 2 circles and one curved surface. Curved surface area will be 2 pi r into h. This is the surface area of a cylinder, by the way, very standard formula. Now, since this surface area, let's call it s. S equal to 2 pi r square plus 2 pi r h. Okay. Now, we have to optimize this surface area. We have to make it minimum. In this particular problem, we have to make this minimum. Okay. So, but this surface area is not in single variable form. We have to make it in single variable form. So, other conditions, what we have? Conditions that total volume should be 1.5 liter. This we can also write 1500 centimeter cube. Okay. In liter you can multiply by 1000 to make it centimeter cube. Now volume of the cylinder, what the formula for this volume of the cylinder? This is pi r square into h. This is the total volume of the cylinder, that is pi r square h equal to 1500. This is our condition. Okay. From here we can replace either r or h. So we will see whether which one is easy to replace. If we replace r, then we have to replace at two places, here and here. But if we replace h, that is easier. So we will find h equal to 1500 by pi r square. Let's call it 2 and let's call it 1. So we can write that this using equation 1 and 2. We can write this as s equal to 2 pi r square plus pi r square into h. H is 1500 by pi r square. Sorry, 2 pi r h. 2 pi r square plus 2 pi r h is written wrongly. This is 2 pi r square plus 2 pi r into h. H is 1500 by pi r square. So finally we can write this like this. S equal to 2 pi r square plus pi gone 3000 by r. This is our final function in single variable that we need to minimize. In this particular case we need to minimize. We can write this like that, like this, as function of r as 2 pi r square plus 3000 by r. We have to minimize this. This is our final algebraic form of the function. So now this became an easier problem that we have already solved. How to minimize this? First we calculate first derivative of s. We will get 4 pi r minus 3000 by r square. 1 by r means minus 1 by r square. Okay. Then we equate this to 0 to get critical points. By doing this we can get 4 pi r equal to 3000 by r square, or we can say that r equal to 3000, r cube equal to 3000 by 4 pi, or we can say 750 by pi. Okay. So we can say that r equal to cube root of 750 by pi. So we got this r. Now we have to check whether this r is giving us minimum surface area or maximum surface area. For that we have to calculate double derivative of s. We will get 4 pi minus 3000, 1 by r square. What it will give? Minus 2 means plus 2 by r cube. We will get this. Okay. Now let's put this r here in s double dash r, so that we calculate what is double derivative value at this particular r. Okay. This is our point of interest here. We are putting this in this double derivative. So we are going to get 4 pi plus, and anyway we are going to positive value itself because this is positive. Whatever we do here we are going to positive only. So it will give you something greater than 0. So it is going to give us minimum value. This is what we were expecting. So we can say that we can make cane of radius r equal to cube root of 750 by pi and height h equal to h. Already we had a function in r and h right here, right? 1500 by pi r square. So we can write here 1500 by pi r square. R we can put from here. So to minimize cost of making. Now you understood, right? This is how we formulate. See, this was relatively complicated problem, but we did it a step by step and without getting confused. We formulated this problem in algebraic form and we solved it a step by step. First we draw the first we made the diagram to understand what this problem is saying and what our goal is to calculate in this problem, and then we defined the variables. R and H were the variables in this particular problem, and then variable means unknowns. We have already defined it. We defined these unknowns, and then third thing that what we did is we defined our optimization function. Here in this particular case, it was surface area that we needed to minimize. So we wrote surface area formula, and this was relatively easy formula for surface area of cylinder. Now after that we manipulated these variables to make it function of single variable using the condition that were given, that total volume should not exceed 1500 centimeter cube, and using that we found surface area in terms of single variable in R only, and then this is simply a function of single variable that we needed to minimize. So first we calculated first derivative, and later we checked whether the first derivative of giving us radius will ultimately give us minimum or maximum value based on second derivative test, and then we found out that it is ultimately giving us minimum value, and we calculated that radius and height. So this is how we calculate the optimization problems based on first and second derivative test. Using first derivative test also you can calculate by seeing whether the first derivative is changing its sign from positive to negative or negative to positive, and or otherwise you can just calculate the second derivative and check its sign whether it is positive or negative. Now one more thing I want to clarify: what happens if second derivative becomes 0 when we put r equal to some value, let's say a, and this second derivative also becomes 0, it does not become any positive or negative value, then what will happen? In this case we say that second derivative test failed. We are not able to conclude whether it will give us minima or maxima based on second derivative test. So we say that second derivative, let's write it in formal way. How we can write this is what I am trying to say is, let's say first we calculated f dash x and equated to 0, and it gave us roots, let's say x1, x2, all these value. Then we calculated f double dash x. At all these x1, x2, it gave us 0, did not give positive or negative values. This may happen, right? In that case we say that second derivative test failed. To indicate maximum or minima, right? So we say that second derivative test failed. We go for higher derivatives like third derivative and then fourth derivative, all these tests that we will cover later when we get time we will also see those things. Now in this topic this much only, and you have to practice a lot since this is a mathematics topic. Once you understood the topic, the concept, you have to practice a lot to understand in more detail, and so that you don't make any mistake in the exam. So go to mindspaneducation.com. We will put a lot of practice problems matching GATE standards. So go there and do the practice. In this video this much only. In next video we are going to cover one more topic in this series. Till then, happy learning. See you later.